Here in this video, we're going to look at a couple more examples of taking the derivative implicitly. And the first example here says we want to find dy dx, and then we want to evaluate this at the following point of 2, 3. So we're given x cubed plus y cubed equals 6xy minus 1. So we're going to start off by taking the derivative of both sides. And our variable matches up, so the derivative would simply be 3x squared. And then notice next we have y cubed, so we take the derivative. We have 3y squared, but then the derivative of y. Now again, we could simply write y prime. This example, I'm actually going to write this as dy dx. And then for the right-hand side, we have 6xy minus 1. And you'll probably notice that here we're going to have to use the product rule. We have 6x, so I'm going to group 6x together and multiply that by y. So the product rule says we're going to take the first term, 6x, multiply this by the derivative of y. Well, the derivative of y, once again, it doesn't match up with our variable x. So the derivative would be 1. And then we would take the derivative, which would be dy dx. And then the product rule says plus the second piece, which is the y, multiplied by the derivative of 6x, which would be 6. And the derivative of negative 1 is 0. Step 2 is we want to collect dy dx on the same side. So we have our 3y squared dy dx. And we want to move over the 6x, so that's minus 6x dy dx. And everything else will go to the right, so we need to subtract the 3x squared over with the 6y. So we would have 6y minus our 3x squared from over here. And now we have our dy dx together, so we can simply factor out dy dx, where we're left with 3y squared minus 6x. And once again, at this point, we have everything factored out, so now we can divide everything away to solve for dy dx. So we're left with 6y minus 3x squared, all divided by 3y squared minus 6x. Okay, so here we have our derivative, but recall now, at this point, we wanted to evaluate the derivative at the point 2, 3. So if we plug in the point 2, 3, we would have 6 times our y value is 3 minus 3 times 2 squared divided by 3y squared, so that's 3 times 3 squared minus 6 times 2. And if we simplify this, you would eventually end up with 2/5. So this here would be our slope at the point 2/3. So your tangent line at the point 2/3 would have a slope of 2/5. Or we could say the rate of change of y with respect to x here, the dy dx, at this point is 2/5. Okay, so don't forget that once we find the derivative, we're actually finding the slope here, or that rate of change of that tangent line at the point. So in this case, the point is 2/3. All right, our next example here, notice, this one's a little different. They want us to find, now this 2 here, they want us to find the second derivative of y. And the 2 on the bottom is dx2, means each time we take the derivative, we're taking the derivative with respect to x both times. So once again, we'll start out. We'll take the derivative of both sides. And the derivative of x squared would simply be 2x. And then we have our y squared. So that means we're going to end up with 2y dy dx. Okay, you have to use the chain rule. And then, of course, the derivative of our constant, the 25, would simply be 0. All right, so this is pretty straightforward. Now we need to solve for dy dx. So we have 2y dy dx. Subtract over the 2x, we get a negative 2x. So if we divide, we have dy over dx. We'd have negative 2x over 2y. And if we simplify this, the 2's would cancel out. And we would simply have a negative x over y. So this here is the first derivative. Dy dx equals negative x over y. And now we need to take the derivative again. Well, to do that, we would take d dx of both sides. And when we take the derivative of the left-hand side, we're just going to end up with our second derivative here. And keep in mind, if you were using the up here, instead of dy dx, if you were using the y prime notation, then when you take the derivative here, of course, you would just have y double prime. So this here could, instead of using the dy dx notation, this here could simply be y double prime. All right, so the left side is the second derivative is equal to, now we have this negative x over y, which this is going to cause us to use the quotient rule. And to do that, we have this negative sign out front. Just to make things easier, I'm going to go ahead and leave that negative right out front of the entire problem. The quotient rule says then we're going to take the bottom piece, which is the y, and multiply that by the derivative of the top. So the derivative of x would simply be 1 minus the top, which is x, and then the derivative of the bottom would be 1y, or dy dx. Okay, so we take the derivative of the bottom. Remember, the derivative of y would be 1, and then we have to take the derivative of y, the chain rule, so that's dy dx. And the quotient rule says all of this is divided by the bottom squared, so we end up with y squared on the bottom. Alright, so if we simplify this a little bit here, of course y times 1 is simply going to be y. And if you notice here on the top, we have y minus x. We have our x term. But then we have this dy dx. Well, this is the derivative of y with respect to x. Well, what does dy dx equal? Well, dy dx is what we found up here above. Or dy dx is equal to the negative x over y. So in place of this, I'm going to substitute negative x over y. Okay, so here we're just simply using our substitution, dy dx. From up here, we're going to substitute in negative x over y. Now the advantage of doing this, if you notice here in this problem, we have a y, an x, dy dx, and a y. So basically we have three variables. We have the y, the x, and the dy dx. So if we get rid of the derivative here, dy dx, using substitution, we know the first derivative is negative x over y. So now our problem contains only x and y terms. So this is all over y squared. And of course, don't forget this negative sign out front. Make sure we bring that down. And if we continue to simplify the numerator, we have y minus x times x, or in this case actually we have a negative here, so the two negatives would make this a positive x squared over y, and this is all over y squared. Alright, so now if we want to eliminate the fraction, we could actually multiply the numerator and denominator by y, and that's going to eliminate the y here. So we're going to end up with y times y, which would be y squared. And then x squared over y times y, the y's cancel, so you're left with x squared. And on the bottom, we have y squared times y, which is y cubed. And we still have the negative out front. And at this point, do you notice anything that we can do with this problem here, particularly with substitution? And maybe if you look at the y squared plus x squared, do you notice anything we can do here? Well, if we go all the way back up here to the original problem here says x squared plus y squared is equal to 25. So we're going to substitute 25 in for x squared plus y squared. So we have 25 over y cubed with our negative out front. So here we end up with our second derivative, and notice by doing all this substitution, our second derivative is in terms of one variable y. And you're going to notice, particularly with some examples where it's to your advantage to do some of this substitution here, where we took dy dx, substituted in the negative x over y, and then once we simplified more, we were able to come up with an expression that matched something in the original problem up here, x squared plus y squared equals 25. So be aware that you can do this type of substitution. So in particular, if you're looking at some of the practice problems or your quiz problems on Blackboard, you're going to probably see some of those multiple choice answers using this type of substitution. So if your answer contains x, y, and dy dx, then you're probably going to have to do some type of substitution to eliminate some of your variables, possibly to match up with one of the correct answers.